Hi, my name is Bolin Dutt. I'm pleased to present our work on safe navigation and obstacle avoidance using differentiable optimization-based CBF. Constructing CBFs between two geometric shapes has been a challenging task. In this work, we propose to compute the CBF for geometric obstacle avoidance tasks using a differentiable conic optimization problem. For two convex objects, A and B, the differentiable conic optimization problem computes the smallest uniform scaling factor such that the scaled version of the two objects still have a non-empty intersection. We then use this scaling factor to construct the CBF as alpha minus beta, where beta is a scalar that is larger than 1. For robotic applications, robots and obstacles are often rigid multi-body systems. We represent each rigid body using convex primitive shapes. Then, using the proposed CBF construction method, we write a CBF for each robot obstacle rigid body pair within the robot's workspace. Additionally, a performance controller is used to generate a reference control UREF. Then, a CBF QP using the constructed CBF is deployed to filter the reference control and obtain the safe control action. We first demonstrate the efficacy of our approach on a mobile robot example with a capsule-shaped mobile robot and polygon obstacles. We assume that we can directly control the robot's linear and angular velocity. Using our proposed CBF with a simple PD performance controller, the robot generates fairly complex maneuvers to ensure safety. We compare our method with the SDF-based CBF QP controller. When using the SDF-based controller, the mobile robot gets stuck when getting close to the obstacle, and the SDF CBF QP often fails to find a feasible solution. This is due to a reduced feasible set caused by the conservativeness of the approximated partial derivative of the SDF in the CBF constraint. For the FR3 robot, we first show the results on the 3-block task, where the goal is for the robot to reach a point within the lowest block. We can see that in simulation, the end effector reaches the closest point to the target that avoids collision. We show the same scenario, but on the real robot. For the 2-wall task, the goal is to bring the end effector to a point in between the gap of the wall and the back. We show the same scenario on the real robot. For each experiment, we recorded the CBF values of each link obstacle pair, and for each obstacle, we show the minimum CBF value among all the links. We can see in both experiments, the proposed differentiable optimization-based CBF controller is able to guarantee safety in both simulation and in the real world. In conclusion, we present a systematic and computationally simple approach to construct CBFs using differentiable optimization-based collision detectors. On the theoretical side, we showed continuous differentiability for strongly convex scaling functions when the gradients and Hessians exist and are continuous. We conjecture that the continuous differentiability can be generalized to one object being strongly convex and the second one being only convex. We experimentally demonstrated the efficacy of our approach on a mobile robot in simulation and a 7 degree of freedom robot manipulator in both simulation and on the real robot. Thanks for listening. For more details regarding the proposed differentiable optimization-based CBF, please refer to our paper.